Welcome to the videos of Chapter 5 of the Crystal Clear Electronics 2 curriculum. In this chapter, we will discuss the hardware abstraction layer in more detail, explaining what it means, how to use it, and why this particular HAL will make your life easier. Today's presenter is Szabolcs Vereb, an electrical engineer currently working as an assistant professor at the University of Technology in Budapest.
Welcome everyone! In the videos, I'll be assisted by Zalán Gyurica, an electrical engineering student at the University of Technology, also in Budapest. As Zalán mentioned, today we will learn about the hardware abstraction layer. This will teach us a new approach, as in our projects, we try to separate the application and the hardware-dependent parts. This might sound weird at first, but if you understand the concept, you will find it much easier to get on with it.
That's right. Of course, we have also brought a practical example. We will write an LED blinking program together. We want you to be able to try it out too, so we're not using the so-called guitar panel from the veteran curriculum, but the Nucleo development board, which is marked F446ZE. This is much easier for you to purchase. You will find this panel in the components list on the website.
We've also prepared an extra video to show you how to port a project. This means we'll demonstrate how to transfer a project from one microcontroller to another. Stay tuned for the videos of Chapter 5 of Crystal Clear Electronics 2.
Let's get started with today's topic. Can you tell us what this hardware abstraction layer is all about and why we are dealing with it at all?
The hardware abstraction layer, or HAL for short, is used to make all hardware functions available to the programmer without the need for specific knowledge and study of the hardware. In effect, it is a software library that sets the registers on a device according to a specific logic, thus hiding from the programmer the exact way in which the registers are set.
The hardware abstraction layer will be hereafter referred to by the abbreviation HAL, which is used because of the English initials.
In this picture, which we will show you in a moment, you should imagine the system as follows. Our example applications written on a microcontroller usually need to reach various peripherals such as ports and timers. We can normally do this by writing and reading registers from the program. It is a bit inconvenient for us because we need to know the exact address of these registers in the microcontroller, and we also need to know the meaning of each bit in the register. Of course, this information is available in the datasheet of the microcontroller, but usually, these documents are thousands of pages long, and sometimes it takes a lot of time to find the necessary information. This is the problem the HAL was designed to solve. It basically provides a set of descriptive functions for writing and reading registers that we can call from our program. As you can see in the figure, HAL is between the application and the hardware.
The role of the HAL is very important in ensuring the software's portability. Portability means that the software or parts of the software do not have to be rewritten if you run the code on another device. For embedded devices, this rarely means that the entire software can be used on another device without modification. In general, the aim is to minimize the need to rewrite parts of the software if, for example, you want to use a different device within the same family of microcontrollers. There is little overlap between the HAL library functions of different manufacturers, so the code is usually not portable when changing families.
Let's take a step back from our embedded system and think about what a hardware abstraction layer might mean for a computer. Let's say we connect a mouse to a personal computer or a notebook. The program on the computer only needs to know what you click on and which button has been pressed so that something can happen. It doesn't matter what the brand of the device is, whether it's lit up or whether it has a USB or some kind of wireless connection. For computers, the above functionality is provided by drivers.
The role of the hardware abstraction layer is very similar. It provides information important to the application by masking the physical operation, and hardware devices can even be replaced.
Suppose you want to blink an LED with your development board. For the application, we are only interested in which LED is lit and for how long. It doesn't matter to us which bits of which registers are used to achieve this. The HAL is, in fact, a library of functions that can be called to access various hardware functions.
It's worth getting familiar with the Application Programming Interface, or API for short, which is often used in programming.
This term refers to an application that is available to external programs that others can use. It does not mean a graphical interface, but functions and variables that can be called from outside by another programmer without any internal knowledge of the program based on the documentation. Our development board contains an STM32 microcontroller made by a company called ST. To simplify programming, the manufacturer provides the STM32 HAL library. As you can guess from the name, this is a HAL for STM32 microcontrollers, which is an API to access the microcontroller's functions.
From now on, we will use the STM32 HAL library, but it is not the only library that can be used as a hardware abstraction layer. It is a good starting point because it is free and covers all functions, but it may contain bugs. Anyone else can write such a library, but of course it is a huge task to build one, so it is not always worth doing it even for larger projects. Of course, you can also choose not to have a hardware abstraction layer, which means that you set the registers directly when developing your application. However, in this case, we need to know exactly what the registers do, and it will be very difficult to run our program on a different type of device, and we will probably have to rewrite it completely.
In the LED blinking example code shown in the previous chapter, in chapter 4, we achieved the desired lighting effect by writing the registers directly. Let's create the same application, this time using the HAL functions. The structure of the program is shown in this figure. The main part of our application, the LED blinking, will be implemented in the main.c file. No other C and H files will be needed due to the simplicity of the program. From this file, we will call the necessary HAL functions that will set the corresponding pin of the GPIO port of the LED to logic high or logic low.
During application development, the source files in the HAL library are very rarely changed and only needed for more complex applications. For almost all example codes, we will modify the files in the application category. We also do not modify the values stored in the registers. This is done by the HAL functions.
Let's see what this theoretical structure looks like in practice. Here we can see the structure of a project using the HAL library, using the Project Explorer in STM32Cube IDE. Note that the files for the application are under the Core menu item, and under the Drivers tab, those belonging to the HAL library.
In the upcoming video, we will start writing the LED blinking program using the STM32 HAL. See you there.
See ya!
See you!